lecture. There will be an algebraic geometry seminar dinner tonight, and if you're interested, we'll make arrangements after the talk. So, the second lecture on families of algebraic varieties.
Okay. Thank you very much. And so let's just recap where we ended up yesterday. So the main question that we were trying to study, what is a good family of algebraic varieties? And then the part 2 is, can we describe all good families in some optimal manner? And we paid special attention first to hypersurfaces, and then we looked at curve, and we ended up with the Lin-Mumford compactification of the moduli space of smooth curves of genus G. And this space parameterizes stable curves. And so these are projective, connected, and reduced curves. So that these are sort of the simple assumptions that everyone would say. And then the key conditions that we impose, there is a local condition that this curve should have adverse nodes, at least locally, analytically. They should look like the two coordinate axes in the plane meeting. And there's a global condition that omega c should be ample. And we went through a little bit what exactly is omega c, is just a reminder of the various approaches, because these will come in handy. And so now we would like to move to higher dimensions. And so the first question is, what are the correct analogs of smooth projective curves of genus at least 2? And then what are the correct analogs of stable curves? So these are the two questions that we want to investigate. And sort of we noted already that it is not too hard to consider a moduli problem that gives you a reasonable open moduli space. But if you want to make sure that the compactification works right, then somehow you really have to get the notion right. That's very delicate to have a good compact moduli space. Open moduli space relatively easy to get. Okay, now it turns out that when you want to compactify, then the key question is to understand what happens with one parameter families. And so the basic setup is that I have a smooth curve. You can even think about it as the unit disk. If you like, we specify a point in it, I denote it by 0, and then the complement of this will be B upper 0. And then we assume that on this open set B0, there is a family of our favorite algebraic varieties. Then what we would like to do is to extend it to a family over B. Yeah? So that we have this family over B0, we would like to extend it to a nice family over B. And then we hope to do it in a unique way. Okay? And so then that would suggest that this limit is that, so the fiber over 0, I consider the limit of the other fibers, and we manage to then isolate this sort of optimal limit of these varieties. Now there is one small point that it is that already for curves it is frequently not possible to do this over B, but you have to take a ramified covering of B first. So this is caused by the automorphisms. If there are no automorphisms, then you don't need to take this covering, but if the limit is expected to have some automorphisms, then such covering might be necessary. Okay. Now, and so of course you might say that the first thing you could say that of smooth projective curves, higher dimension, maybe you should look at something like just smooth projective surfaces. And then, well, the curve should have genus at least 2, so maybe you say surfaces of general type or something like that. That doesn't matter exactly what general type is, but this is somewhat delicate, okay? And I do not try to write on the board, so you have to imagine that I start with just a trivial family of surfaces, and that here is just your favorite trivial family of surfaces, and then you take a number of sections that pass through one point over where the fiber that I want to do something interesting. And now then I will just blow up these sections. Now as long as the sections are disjoint, on the fiber I just blow up 3 points. So there is just a unique thing to do. But then if you try to understand what happens where the sections meet, then you can blow up the sections in sort of different order. First this, then this, and third this one, or you can do it in some other order. My question is, do you get exactly the same limit? And actually, what happens is quite interesting. If you have 2 sections, then the surface you get in this fiber, if you do it in first this, then this, or the other order, the surface is the same, but the total spaces are not. And if you have 3 sections, then even the isomorphism class will depend on exactly in which order you blow up these sections. It's an interesting computation to do with blow-ups, okay? And so that means that if you want to look at smooth surfaces where you blew up at least 2 points, then there are these various problems that when the points want to come together, you will not have a unique limit, okay? So then, of course, the answer is that, well, maybe you should look at surfaces where you did not blow up any points, and so these are then the minimal models. But they still have some other their problems. We want to look at actually something even better, namely the canonical model, okay? So let's try to do this for arbitrary smooth projective variety. Let's assume that you are just walking peacefully and you encounter an n-dimensional smooth projective variety just sort of floating around, and then you would like to somehow grab it, to get some hold on it. Yeah. So then you would like to embed it into some projective space, yeah? And then you can start write down equations, everything. Now, how do you embed the variety in a projective space, also the map to projective space, where you have to start with a holomorphic line bundle, L, and a bunch of sections, and then at each point you just evaluate the sections. Of course, the fiber of a line bundle is only a one-dimensional vector space, so when you evaluate, you get things that are defined only up to scalar. That's why you end up in projective space and not in affine n+1 space. Now, but of course, for this you need a line bundle, and then the only line bundle that you can reliably find on an algebraic variety is this line bundle omega x. So you can then think about it as a line bundle about the holomorphic n forms, or if you prefer the tangent bundle, you take its determinant and you dualize it. So there is this line bundle, and of course then you can have its powers. But so the many algebraic varieties, these are the only line bundles, okay, that you can get. And so even if there are more line bundles, if you start to look at the families of algebraic varieties, the other line bundles you frequently cannot put together into families. This is the only one that you can reliably write down, at least on families of algebraic varieties. There are actually theorems of this that's what I said is really the case. Okay? And so now then, once you have this line bundle, we can take its powers, and then for each power I can take a basis of in the space of sections, and this map the variety into some projective space whose dimension increasing very fast. And now the claim is the very nice thing that happens, that the images, or maybe precisely the closures of the images, they stabilize. Yeah. So that if you look at M that's sufficiently large and is sufficiently divisible, I try to use those two vertical lines to indicate sufficiently divisible. Then you get something that does not depend on M, okay? And then this variety is then called the canonical model. So it, of course, can happen that it has sort of smaller dimension than X. We will not be interested in this case, and maybe in that case people don't really call it the canonical model. But sort of as long as this is the case. And then also another the nice thing is that if you start with any other variety that is birational to X, you end up with the same canonical model. Okay? So that means it is some isomorphism class that you can associate to a birational equivalence class of smooth varieties. Now, this theorem that I stated here, it was actually pretty slow to get proved. So, when the dimension of X is 2, then Henrik has proved something quite similar to this. So I think so the final step was written down by Mumford, but maybe it was actually pretty well known by that time, and he just wrote it down because there was no proof in the literature. So, and now, then sort of after this, it was maybe even generally believed that this theorem is not true in higher dimensions. At least there were some indications that this might not be true. At least people did not think it was true. So then the large breakthrough came with Mori, who first envisioned a program that this should exist in dimension 3, and then he proved that they exist in dimension 3. And then in higher dimensions, the final step, maybe the biggest step, was done by Heikkinen and McKernan, but lots of other people contributed to it, first Birkar and Caccini and others. So anyhow, so now we know that these canonical models exist, and so the one of our thesis is that these are the right analogs of smooth projective curves of genus at least 2. Okay. So now they have one problem, though, that these canonical models, they are singular. Yeah. And so far we have mostly looked at smooth varieties, but then we have to look at singularities a little bit, and I try to go easy on the singularities that come up. So I might make some statements that are not completely true, but sort of true at least in spirit. Okay, so if you can prove the Riemann hypothesis using one of these statements, maybe you should check with me just to be on the safe side. Okay. Okay. So then the usually the main question is how to write down this sheaf omega. So if I have a singular variety, then of course over the smooth set, I can write it down. I start with the tangent bundle take its determinant, and just dualize it. But sort of this doesn't show too well what happens near the singularities, and we will be very interested in exactly how this bundle behaves near the singularities, and especially how can I write down some kind of a global section of it. Okay. Now, it is fairly straightforward to do this for hypersurfaces, and so, okay, so this F should be that G. Yes, sorry. Okay, so maybe it's not as easy as I thought, but with some small changes, one can write this down. So these are defined. So you see that if you look at this, that it's not defined where this derivative is 0, but they agree over the overlap, and where all derivatives are 0, that's exactly the singular set. So this really writes down a nice generator outside the singular set for an affine hypersurface. Now, the another thing we are interested in, that's an example that comes up a lot when you start with Cn and we take this quotient with a finite group of linear transformation. Maybe we assume that the origin is the only x point, but at least that should not have a codimension one Higgs locus. Then in that case, for this quotient, well, of course you would like to say that sort of this obvious generator of omega on C and descends. But if the group action is non-trivial on this is transformed by some character, then it will not descend if this character is non-trivial. And so that means that this will not descend, but some power of it descends where M is exactly this G mod G intersect SLN. So that's okay. Omega itself is not as nice, but at least some power of it has a nice global section. And then the third set of examples that is good to keep in mind is just cones, that you can take a cone over a Fano variety or maybe a cone over a Calabi varieties. These are particularly relevant for us. And now, for some time, there was a belief that sort of these are really fairly typical among the classes of singularities that we have. So it is not that the singularities that we will face, they are in these, but I think people didn't know any statement that was true for these three classes, but not for all of the singularities that we look at. But then a few years ago, some new examples emerged which disproved various conjectures. So maybe with the singularities are more complicated than these, but I think that for our purposes, just to keep these three classes in mind, that's really all we need. Okay, and so now to understand our singularities, well, our plan is that we look at birational maps. So, for instance, for start, I have x and y are smooth, and I have this morphism between them. That's an isomorphism over some dense open set, but might have some positive dimensional fiber. And then the key is to compare the dualizing sheaf on the source and the pullback of this dualizing sheaf on the target. Now, in the smooth case, this is well known. We teach it in some engineering math courses. And so you just pick local coordinates, and then you have the pullback of a section of the dualizing sheaf is just the Jacobian of f times the natural selection you would write down x. And so now the way I would like this with this line bundle, that if I just pull back this omega y, that's naturally it's contained in omega x, and so how much smaller it is, that exactly the ideal that's locally given by the Jacobians of f. Okay, so the main thing is that this f up omega y is contained in omega x. Sorry, oops. Okay, And now then there is the inverse function theorem that is more precise, that the point is not contained in the support of the Jacobian ideal. Maybe I should say it's a quotient, theta circle. So, yeah. If this f has a local inverse at P. Okay. And so now then, we would like to move to the singular case. Here I want the source still to be smooth. Usually if we start with some singular variety y, the x will be just some resolution of singularity, and so smoothness for x is not a particularly big issue. And then there will be some exceptional set where this map is not an isomorphism, and I would like to compare f upper star omega y and omega x. And now there are unfortunately 4 classes of singularities that we have to live within this business, but I just want to show you that they have some very natural definitions. And so the first one is the smallest class, the terminal singularities, where the inverse function theorem holds. Okay, so this is really the simplest that you just want to say that this is nice. Now then the other is the canonical thing, where you just want to make sure that the pullback of omega y is contained in omega x. Okay, so there is something like the Jacobian ideal, though maybe the way to write it down might be more complicated. Now then there are 2 classes, and so here this f upper star omega y is not contained in omega x. It is something larger, but if you pull back this omega y, it picks up at most simple poles. Okay, so this E, just everything comes there with multiplicity 1. So the pullback has at most simple poles. And now there is this mysterious thing that you look at the pullback of omega y, then it has poles of order less than 1. Now you might ask, how is that possible? And there was this thing that in the quotient case, for instance, we computed that omega y itself is not really a line bundle, but some power of it is a line bundle. So that means that technically I would apply this not to omega y itself, but omega y to the m. And so then of course this would change, E would change to ME, so then this is 1 minus epsilon that's contained in m minus 1 times E. Okay? So then that means that if I scale down, then it looks like it has a pole of order less than 1. So for instance, you would say that the function in the square root of 1 over square root of z, I would say that it has a pole of order 1/2 at the origin. So it's some statement like this. Now this last class is especially nice from differential geometry point of view, because this is equivalent to saying that if you take a section of omega y, then of course you can sigma, then you can look at the sigma wedge sigma bar, then it's a volume form. There should be a power of I in front of it before it becomes an actual real volume form. And then this condition says that the volume in the integral is finite, that if you just integrate over the smooth locus, you get something finite. So because of this, technically this is the class that we really like, okay? But unfortunately, we almost always end up in the log canonical case. Yeah. But so there is this little epsilon that we have to fight here. That is technically actually quite challenging sometimes. But okay, and so now maybe you are not surprised that the canonical models, they have canonical singularities. They were named at the same time by Miles Reed. So at least this is make sure. And so then the canonical model is a some variety that has canonical singularities, and omega y is ample. And then, in fact, if you write down any smooth variety that's birational to y, then y ends up the canonical model of x as we defined earlier. So there is an internal definition of the object whose moduli space we would like to get. So there's a local condition that they should have canonical singularities, and there is a global condition that this omega y should be ample. Oops. Okay. And so let's see how can we actually prove that this holds. So we claim that the sections of omega y, they are the same as the sections of omega x. And since so this holds for any powers, and since we are mapping with some basis of this space, and so that's the same as the basis of this, so we get the same image. Now, by the definition of canonical, this one holds, so that means that the left-hand side is contained in the right-hand side. Now, conversely, let's pick any section here. Now, you see this map is an isomorphism over an open set, so this phi x, you can view this as a section of omega y to the m. Well, of course, possibly it can have some pose along the image of the exceptional set, where this map is not an isomorphism. But you see the image of the exceptional set has codimension 2, and the pose always appear in codimension 1, so that means that in fact we get a section downstairs. Okay, so this is why we like these objects, because they really appear as the canonical models of smooth varieties. Okay, and so now let's go to the uniqueness of specialization. So you see, we are back into this situation that we wanted to understand. So we have that smooth curve B, and assume that outside the marked point called 0, there is already a nice family of canonical models, and then we would like to extend it across the origin. And then the claim is that there is at most one extension with the property that y, the total space that has canonical singularity, and omega y, I think so technically it's better to use the relative to omega. It's not really important for us, but sort of is ample on every fiber. Okay, and now you see this should be exactly the same statement that the canonical models are unique. Okay, sort of just a relative version of exactly the same statement. Okay, so that means that if we would like to get a unique extension, then we would like to make sure that omega y is ample on the fibers. This would be a fiber-wise condition that just says that for each fiber, omega is ample. And we have to make sure that the total space has canonical singularities. Okay. And so, so how to make sure that the total space has canonical singularities? Well, not surprisingly, we need that the general fibers, they should have canonical singularities. But some special fibers, they might have some worse singularities. You see, this already happened when we compactify the moduli of curves. We have generally smooth curves, and then suddenly we may end up with a node. And the node doesn't really bother us too much. So there is unknown class of singularities that maybe we can have in special fiber. And if we understand what should be inside this, unfortunately it's a blue box, then we will know what kind of singularities should appear on the boundary of our moduli space on the objects. Okay, so in the curve case, we allowed nodes. Now it turns out that nodes are not canonical. They are low canonical. But every time I deform the node just a little bit, typically something x, y plus t to n, then I get a surface singularity that is canonical. And this was known already to Duval in 1934, okay, from some other their point of view. And so then in higher dimensions, I would like to understand. So if you are just looking at one point of the total space, then so here is the total space, and then I have this fiber that is possibly more singular. It's just that's a Cartier divisor. So it is defined by the vanishing of some function. And you would like to have a theorem that you assume that if the complement of D has canonical singularity, and D has these has other singularities, then you would like to conclude that Y itself has canonical singularities. Now, if I just put canonical singularities here, then this is true, but this is not good enough. So here that in the curve case, we could allow some worse singularities, and we still ended up with something canonical for every deformation. And so the question is, what should this question mark be? Okay, this 4 question mark. And their claim is that the 4 question marks are precisely log canonical. Okay, and I mean this claim in actually the strongest possible form. So if I put log canonical here, then this implication holds, and it will not hold for any other singularity. So it is completely nailing this implication, and so that's why then we will say that on the possible limits in higher dimensions, we should have these log canonical singularities. Okay, so let's see if we can at least start to understand why this might be true. Well, let's start with an arbitrary resolution of singularities. Maybe make it nicer various divisors that will come up. Maybe they should be smooth and intersect normally, but that's fine, at least in characteristic 0. And then I can write down, so the canonical class of x, I switched from omega x to kx. So some kx, yeah. So I think you should just think that k is the same as omega, and I started to write things additively. So maybe k is something like log omega or something. Sorry about this. Yeah. And so the canonical class upstairs is the pullback of the canonical class plus then the Jacobian ideal. And then if you pull back that divisor D, then there will be its birational transform, and then there will be the exceptional divisors E. Okay? And now we would like to write down the canonical class of dx. And there is an adjunction formula for that. That is just you have to take the canonical class of x plus dx and restrict it to dx. So this map is exactly the Poincare residue map that I mentioned already for the plane. I just do the substitutions that come from here, and then of course here is ky plus d. If I restrict it to d itself, that's just the canonical class of d. Okay. And so then it's just the pullback of the canonical class of D plus this J minus E restricted to dx. Now, and so this D, if I assume that it's log canonical, well, that means that this J minus E restricted to dx every divisor appears in it with coefficient larger or equal -1. And then, so this is precisely the simple pole condition that we had before. Now this E is of course, why is it doing this? And so that I pull back a divisor D, so that means that E, it contains all the exceptional divisors with positive coefficient. Okay, okay. And so that means effective when the integral, I'm subtracting it from J, I still get larger or equal -1. That means that J restricted to dx is larger or equal 0. Now you see, this is precisely what we wanted, because canonical exactly says that this J is effective. Of course, there is one problem here, that I have proved that J restricted to dx is effective. And so if J, and so that means that J might have a component that is disjoint from dx, but appears with negative coefficient. Then in the restriction, I would not see it. Okay. But it turns out that there are some rather subtle convexity properties for the coefficients of J, and then if you use this, then you know that if you get something that's negative far away from dx, then you should also get it right next to dx. So this was conjectured by Shakurov, and then in increasing generalities was proved over the years. Okay, so that is roughly the proved explanation that we really need the log canonical condition. And so then the stable varieties that should be the analogs of the stable curves, they should be projective and connected and reduced. Well, it follows from the singularities. And there are these two conditions that should be satisfied. So the local condition is that, well, essentially they should have log canonical singularities. The only reason that the semi is there, that people who define log canonical singularities, originally they were always thinking about normal varieties. Yeah? And so that means that by this definition, a node of a curve cannot be log canonical. But if you look at this definition for non-normal varieties, everything goes through, but it's called semi-log canonical when you allow some non-normality. And then there's the global condition that omega x should be ample. And so then the claim is that these are the objects that provide the right compactification for our moduli problem. Now, so then again, just to say, so what are the typical SLC, which is short for semi-log canonical singularities? I already mentioned that we have quotients by finite group, and that there are the cones over Calabi-Yau varieties, and sort of rather typical non-normal example is just look at the coordinate hyperplanes in Cn plus 1. So it's again not surprising that these have to be allowed. Okay. And so now we claim that sort of with this setup, we had uniqueness of specialization already, we understood them, but now we need also the existence of specializations. And sort of here is essentially the proof how to construct it, that so if you start with a family y0 over b0, just extend it any which way first, so don't even worry about the singularities, just anything that now it's a projective morphism. And then you resolve the singularities, okay? And then you write the central fiber that I'm interested in is the linear combination of these irreducible divisors. Let's assume also we can that the di's are smooth and they intersect each other transversally. And now we need to take a base change. I mentioned that it's necessary. The only thing you have to make sure in characteristic 0, the ramification order at that point 0 is a multiple of all these mi's, okay? So you just take this, and then you get and so then you do base change, and you take its normalization. Then you have this y3 to c, and now the central fiber is now reduced. So everything there appears with multiplicity 1. And then you just take the canonical model of y3, and that's what you want. Now, of course, when I say they take the canonical model, there are some hard theorems about the existence of the canonical models, but the rest of it is just actually very much the same as one could do it for curves in characteristic 0. So in fact, the general outline is the same. Okay. And so then, here is the diagram. I have a start with this family, and I have to make this base change. Then still you have this over an open curve, and then you can extend it. And now we check that y has canonical singularities. This follows from our previous computations, and omega y is ample on every fiber. Okay, so then this is the main step one needed in proving that the moduli spaces exist. So we sort of end up with the main existence theorem. Well, that there will be some other party that needs to prove that we fix some positive n and d, and then the claim is that there is a projective moduli space m n d bar, which parameterizes stable variety x of dimension n, such that the self-intersection of the canonical class is D. Okay, so in the curve case, one typically uses the genus. Instead, we could have used where the degree of the canonical class is just 2 times the genus minus 2. So aside from this is really the sort of the same type of claim. Now, while these spaces have some good properties, as far as the moduli properties are concerned, they are as good as for mg bar. Yeah? So that is the good news. The bad news is that as varieties, they seem to be much more complicated than mg bar. So one thing nice about mg bar is that the singularities are mild, and it has some very interesting structure. Whereas in higher dimensions, well, we get some moduli spaces, we have existence, but for instance, we know that even already for just smooth surfaces, without going to the boundary, these moduli spaces, they can be arbitrarily singular. So there is this is a result of Vakil. And for instance, even the number of components is not known. There are a handful of cases where, but I mean really handful probably, where actually people, especially Alexeyev, they understood. So I've asked a few cases, but it's very hard to work with them. Now, why is it hard to work with them? Sorry, before I explain that, maybe I want to say something about the history of the proof. So for surfaces where the background is that we need the existence of canonical models, which is essentially the same as the minimal model program for 3/4. This was done by Mooring. Now, then the definition and the proof of existence of these moduli spaces, it's in a paper of myself and Shepard-Barron. And then these things I said about specialization, the specializations, they exist and they are unique. That means that these moduli spaces, they satisfy the evaluative criterion of separatedness and properness. And so they are separated, that's fine. But you see, a scheme that satisfies the evaluative criterion of properness is proper if it's a finite type. And for some time it was not known that they are of finite type. And so, but for surfaces, this was proved by Alexeyev, and then the projectivity it was proved by me. In higher dimension, where the background is more complicated, so we rely on several results of Haken-McKernan, and then some more complicated recent results of Haken, McKernan, and Shu. Then the existence is, there are some issues, but it's not too bad. I might have time for a few of them. The properness was actually much harder. It's a recent paper of Haken, McKernan, and Shu. And the projectivity, the hard theoretic aspects were settled by Fujino a few years ago, and then the final proof is by Kovac and Patakvalvi just last year. So as far as the general existence results, we are in good shape. But as I mentioned, it's pretty hard to describe these spaces explicitly. Now, what's the problem with properness and with boundedness? So what could go wrong? Well, so for instance, you know that you just start with some smooth projective curves, and in the limit you get some reducible curves. Yeah? Now, for curves, the singularities are just nodes, so you cannot get to the more and more complicated singularities. But maybe you can get more and more irreducible components, and so then if for fixed genus you can get more and more irreducible components, that would be a serious problem. Then you couldn't have a compact moduli space. But you see, this will not happen for curve. Why? So if I have a reducible curve, I write it as the union of Ci, Pi, where Pi denotes the nodes, okay, then the degree of the canonical class, or omega C, is just the sum of the degrees that you get on each irreducible component. And then on each irreducible component, you have a line bundle, which is ample, so it has a positive degree. That means that I sum things that are at least 1. And I know that this is just 2g minus 2. So you know right away that you get at most 2g minus 2 irreducible components if you look at a stable curve of genus G. Well, could we do the same thing, for instance, if we are on a surface? Well, so then again, I write it as the irreducible components themselves, and then here the components, so where two curves used to meet at a node, here two irreducible components, they typically meet along some curves. And so that means that then if I restrict the canonical class of this to an irreducible component, I get the canonical class of Si plus this curve di. And again, I have this formula. And so now everything looks nice, but what's the problem? Well, the problem is that these numbers, they are, all I know about them at the moment, that they are positive, but they can be rational. You see, the problem is, if you think of the quotient singularities, then I get some things that are not exactly Cartier. I know that some power of it is a line bundle, and that has an integral self-intersection. But here you can get some rational self-intersections. And so, for instance, if you start with the weighted projective plane and you take on it a degree 7 curve, so this should be D, then you compute that the self-intersection is 1/6. Yeah? And so they can be actually smaller than 1, and if you don't have an upper bound, then you don't know how many components you can get. Now, for surfaces, it was not hard to prove some inequality like this. I don't know how sharp it is, but I think there are much smaller examples like this. But in higher dimension, it turned out to be a very difficult thing to prove. So Alexei did this for surfaces, and Haken, McKernan, and Shu in higher dimensions. So I look at sort of all these pairs here that I get that appear as irreducible components of my stable varieties. So then there is the canonical class, and then there is a divisor which tells you where that component intersects the rest. And then I know that this is ample, so its self-intersection is positive. But unfortunately, it is rational. And it's a very complicated set, but they prove that it satisfies the descending chain condition. It's not a discrete set, yeah? But it has no infinitely descending subset. It has plenty of infinitely increasing subsets that converge to something. For instance, they can converge to 1, so it's not hard to write down things that converge to 1 from below. Now you see, but this means, for instance, that the set has the smallest element. I mean, here for surfaces, we know that this is at least 1/1764. For three-folds, we don't know what an actual lower bound is for this. So the proof doesn't give 1; it's really just an existence proof. But it certainly tells us that if I bound the self-intersection of the canonical class on the general fiber, then I can bound at least a number of irreducible components in the special fiber. Okay, and so it is actually a quite tricky thing to prove that we get something that is of finite time. Let's see. I wish I had a. Is there a count? No, there's no counter here. Okay. Okay. Let's just go. So now, and other interesting thing that's actually worthwhile to think about is sort of exactly how do we get omega c on a curve. So I already told you that if I restrict omega c to one irreducible components, then I get this omega ci, which I know, and then I allow some poles at the nodes. Yeah, but you see, how do we glue omega c from this omega ci pi? So that's actually a non-trivial question. Typically, if you have sometimes two line bundles on two curves, and these two curves meet, then you still have a choice of some isomorphism C star versus possible gluing. Now if they meet at just one point, it's not a problem, but if they meet at two different points, then suddenly you can't normalize them, and you get a C star versus of different line bundles on the union of these two. So why is this not a problem for us? Well, and this is is given by the residue theorem. So you see that if you just look at these, think about it as a unit disk, and then you allow simple poles at the origin, and you compute the residue, then the residue of a section of this is a well-defined complex number. Okay? So that this means that if you look at this line bundle omega ci pi, then the fiber of it is pi is not just a one-dimensional vector space, but it's canonically isomorphic to C. Okay? So to the complex numbers. Now, of course, if it's canonically isomorphic to C, both of them, then you know how to glue sections. Except if you compute, then the way the sections glue is not that they have to exactly match, but in fact they have to be precisely the opposite. So they glue when the residue on one side is exactly minus the residue on the other side.
Please excuse this interruption. This is a test of the in-building voice-capable fire alarm system. This is only a test, and no action is necessary on building occupants. Thank you.
You are most welcome. Okay, so anyhow, clearly the residues were something very important topic. Okay, and so now then there is something similar that happens in sort of the higher dimension, but it's more complicated. That's for every stable of varieties. So on sort of the curves, it was only the nodes that came in, but there are some sort of key points that sort of that play essentially the same role as the nodes played there. And there are some Calabi-Yau varieties of dimension less than dimension x that can be attached to them. And there are some natural Poincare residue maps that you look at omega x and you look at the fiber over pi, it's just the H0 Zi omega Zi. So, of course, in the curve case, the only zero-dimensional Calabi-Yau variety is just a point, and then omega of the point is canonically isomorphic to C, so that's why we see it there. But in higher dimensions, we get something more complicated. And now, what we lose here that this is, of course, only canonical up to the action of the automorphism group of Zi. And so then we need, and I think this is what I would like to finish with. It's a very, very nice proof that this is not as completely a rigidification as we had before. It was isomorphic to C, but sort of here it's sort of up to a finite subgroup we can still declare that it's isomorphic to C. And so the main claim is something that goes back to the line, that if Z is a Calabi-Yau variety, then the action of its automorphism group on this H0 Z omega Z, that is a one-dimensional vector space, that it is finite. Okay? So let's pick an automorphism where it acts with some eigenvalue. And then we would like to prove that this lambda is in fact a root of unity. Well, first G acts on the middle integral cohomology, and by Hodge theory, A0 Z omega Z actually sits there if I just complexify this space. So that means that this lambda will be an eigenvalue of this action on the integral cohomology. Now, then this implies that lambda is an algebraic integer. Okay. Now, then we also know that G, where it's an automorphism, and if I integrate sigma wedge, sigma bar, where sigma is a section, then that's a volume. So the automorphism that preserves the volume. So that means the lambda times lambda bar, that's in fact 1. So lambda has absolute value 1. And now, well, we would like to prove that the same holds for all the conjugates of lambda. Well, so how do I do that? So the Z is some kind of algebraic variety that's defined by some kind of equation. If I just apply to any automorphism of C over Q to it, I get some other algebraic variety where this action will be with the corresponding conjugate of lambda. And so I know about lambda that is an algebraic integer and all of its conjugates have absolute value 1. And then there is an elementary argument, I think it's already in a paper of Minkowski that it implies that it's a root of unity. Okay? So then sort of this plays sort of the same role as the residue isomorphism with C, and it helps us rigidify the situation. Okay. Thank you.
Questions? Thank you very much. So if people are interested in joining the